Welcome to the overview presentation for the SIGTYP 2021 shared task. This year's task focused on robust spoken language identification. This overview will be presented by myself, Badr.
Hi.
And Sabrina.
Hello.
So as Liz has said, this year the shared task is about spoken language ID, which is a straightforward problem. Given a short speech segment, the goal is to determine the identity of the language of the speaker. And spoken language ID could be used in many downstream applications as an enabling technology for multilingual and cross-lingual speech communication. And it could also support the documentation and categorization of the languages of the world. Therefore, we would like our spoken language ID systems to be both speaker independent and domain invariant. And that means that the systems should work very well, even on speakers that were not observed during the training phase. And it should also be domain invariant. And that means even if the speech segments for evaluation or when the system is being used come from a different domain with a different acoustic or recording conditions, we also need the systems to perform very well despite this variability in the speech segments. That's what we refer to as a robust spoken language identification.
A challenge we face is that many languages only have small corpora available, which typically are not going to be uniform in their domain or their speakers. These are not necessarily going to be enough to train current models. Where we do have large corpora available, they'll often be uniform in domain or speaker sets. And so they're not going to necessarily represent the domains or speakers that we're actually interested in. So enter this year's shared task. To address this task of robust spoken language identification, we have taken the CMU Wilderness Corpus, which luckily is one of the more multilingual corpora available with 699 languages. But it is almost exclusively single speaker per language and predominantly male speakers. This is not necessarily going to represent many situations we hope our systems are going to be able to address. So to directly test this, we're going to use different evaluation data than our training data set. So here we've taken subsets of Common Voice and open SLR resources, all of which are publicly available, which represent a wider range of variations. So often this is crowdsourced speech. They're multi-speaker data sets. And what we've done is selected small, gender-balanced, speaker-balanced validation and eval sets. The data then that we've selected comprises 16 languages from 7 different language families. And to clarify, the training data and evaluation data differ in 3 primary axes. So they have different domains, different speaker sets, and often different recording conditions. So we're trying to see if we can build models that'll be able to generalize across these characteristics. So here we have a closer look at the data involved in this year's shared task. So for each language, you can see the family, genus, macro area, and the source of the differing evaluation data. So here you can see that for some language families, we have included both more closely related, so languages within the same genus, and more distantly related languages to test the effect this has on our systems.
And for the baseline for the shared task, we have developed a shallow neural network based on convolutional neural network. And the baseline has 5 layers, 3 convolutional layers and 2 fully connected layers. And it takes a spectral representation of the speech segment as input. And the output is a probability distribution over the 16 languages that we have in our shared task.
Okay, so the participants to this year's shared task span a wide variety of universities and represent 2 composite teams. The first, Anne Larica, is a composite team, whose model combined a variety of different layers placed throughout the model to better address different aspects of variation in our speech signals. Here, they used validation data for adaptation to the different domain conditions found in the validation and eval data. The second team, Lipsia, used a deep ResNet-based model and found that shallower networks, perhaps contrary to our expectations, were shown to overfit this task. And so the added depth was actually necessary. They transformed the MFCC features provided to spectrograms for improved representations for their convolutional-based architecture. And here, again, they used 60% of the validation data for adaptation to the target task. Our final team is a composite based from NTR Labs, which used a modified ASR approach, which is again convolutional based. So we can see a theme across the architectures here. They used a different approach to improve their model robustness using sample shifting in time and perturbations from spec augment and added background noise.
So as for the results of all these teams, we of course have a big table in the report, but I think the important takeaway is that we do score our teams on one overall metric, and that's going to be the macro averaged F1 scores, macro averaging over languages. That said, even if we micro average and even if we look at accuracy, the ranking doesn't really change. So in first place, we have the Lipsia system with an F1 score of 0.508. In second place, the Lyrica system with 0.282, and third place, the baseline system with 0.122, and in fourth place, the NTR system with 0.041. One thing that I will say is you can maybe make it out in the table, only the baseline really wins on no language. So all the other systems are competitive on at least one language. So there is some variety in there. One thing you might also wonder about is with these various performances, where is that really coming from? And luckily, I would say, we are able to confirm that the models indeed are able to fit the wilderness data well enough. So they all reach above 96% accuracy, so much higher accuracy than we see here on that wilderness data. So it's really not that the models are not powerful enough. It really is something about the domains and the speakers and the recording conditions, as the other two outlined before, that makes this task so hard. And that's why I think it's very interesting and somewhat encouraging to see that there is really this difficulty in trying to match it. And we don't really know yet how to do this very well. We can also analyze this performance a little bit more in detail. So what we see here is a confusion matrix, only showing this for the Lipsia system since it's the best one and has the clearest diagonal, but others do look somewhat similar. So we see in the rows, the goal language for a particular sample, and in the columns, what that system predicted. And so some trends emerge. I will say it might be a little bit hard to make out on the slide, but these are grouped by language family. So this explains some of the trends you might see. So the first thing that you will notice probably is that Sundanese and Javanese both are predicted as Javanese by the Lipsia system. And that's something we see in the other systems as well. They both predict both of these languages either as Sundanese or as Javanese, but never really are able to untangle the two of them. Similarly, we see that a consistent theme is that Kannada and Telugu are confused, which makes some sense. You might also see that the Lipsia system also classifies some of the Marathi examples as Kannada and Telugu, but this wasn't quite as clearly visible in the other systems. The third thing that is visible here, that's somewhat surprising, is that none of the systems like to predict Russian as a target language. So here you see that there are very few things that are predicted as Russian, and most importantly, Russian itself isn't. So that kind of makes us wonder, is there something about maybe that particular data set or the combination of other languages that make it so confusable? Another thing we can look at is, do the different systems struggle with the same languages? That is, we can correlate their F1 scores for every individual language and see what happens. Now, this is a lot of plots. I really only want to zoom in on this one because I think it shows the clearest correlation. This is the correlation between the number 1 system, Lipsia, and the number 2 system, Lyrica. And you can see that there are really some languages on which both of them have very high F1 scores, and other languages on which both of them have a very low F1 score. So there really is something about the languages or the data that makes things intrinsically harder or easier to find out.
So in conclusion, this remains a challenging task. It is difficult to generalize across speakers and domains, and this domain invariance is not often necessarily tested. Here we saw that the best system achieved 53% macro averaged accuracy, though it was able to achieve greater than 90% in domain. Here, all of the best systems used the limited in-domain samples for some sort of adaptation. And so our remaining question is, this is not always going to be available. So what can we do to continue to improve model robustness and generalizability in the future when we may not have access to at least some amount of data to fine tune on? And so yes, thanks to all the participants for participating in a very challenging shared task, and we look forward to any future work that continues to build on this.
Yeah, thank you for participating. I hope you enjoyed the task.
Yeah, thanks a lot.